Morning, everyone. So again, today we're just going to start off with a warm-up question. Yesterday we started looking at the alcohol functional group. Let me give you an example of some of these molecules here. If I give you the structure, see if you can give me the word name for it. If I give you the word name, see if you can give me the structure. So let's do that. Let's sub on an OH group. Sub on a couple other groupings. Carbon. And I'll give you one going the other way here. Let's see if you can sketch for me 3-ethyl, cyclo pentane 1-O. Okay. So again, I encourage you just to pause the video, give those two a try, and then we'll go from there. Okay. Assuming you've done that here, most of the naming we've already done. Let's find the longest carbon chain. Let's go from any side to any side. Let's string together as many C's as we can. Okay. You'll notice I'm starting to represent this sort of zigzag with the alkane part. We know that for zigzag here, the alkane is tetrahedrous 109. It sort of kinks back and forth. That's perfectly fine. My longest carbon chain here, in this case here, happens to have 8. I do notice that I have the alcohol functionality, the hydroxyl functionality. So before I say octane, just like a regular octane family, the 8-carbon alkane family, we are actually going to be octanol. Okay, the OL is the suffix, the ending, the parent name for the alcohol group. Remember, the OH group here is more special. Even if I had counted it right to left, where I had branches 1, 1, I have 3, 5, and 6, and whatever. Later on, these are going to be 8, 8. I still want to count it left to right so that my alcohol group actually takes priority. My alcohol group, not necessarily at position number 1, but it happens to be at the smallest number possible. So you could either say octane -3O, or just put the 3 in front here. That just tells you where that hydroxy group is, that special functional group is. Okay. Let's tack on these other ones here. I would imagine that every carbon having 4 unpaired electrons, everything's holding hydrogens. There are a few other substituents here. We have a carbon branch on these sides here. So those are methyl branches. I have 2 of them. It's going to be a dimethyl. I have a bromo branch. I have a fluoro branch here. We just do the alphabetizing. Because that 3 there had to take priority, I'm stuck with these being 8, so be it. So we're going to have 8-bromo. So B for bromo comes first. And then we also have an 8-fluoro. At position 8, there's also a fluorine group. We have 2 methyl groups. Remember, we alphabetize them based on the M for methyl, not on the dimethyl. They show up at 4 and 6. Numbers and numbers are separated by commas. So 4, 6, dimethyl. But based on the alphabetizing, we still alphabetize it B, F, M. And then we go down to the octanol there. Okay. So there's the full name for that there. Lots of information sort of condensed in there. In fact, these halides are also a functional group, but it turns out the alcohol functionality is a more important functional group than the halide group. So that's why the alcohol sort of takes the ending there. We could also classify this alcohol here. This carbon is holding 2 neighboring carbons here. So this is actually a secondary alcohol. Okay. Its behavior will be different from a primary or a tertiary. As you look at this other one here, oh no, they've thrown a ring at you here. Well, we know everything that we need, okay? So ring of 5 carbons, having alcohol. It has the special position of position number 1. So let's just sketch a ring here. Not necessarily symmetrical, not necessarily flat or pentagon, but we see that rings that are nice and large like this, the bond angles can be a little bit more stretched out. That's nice for it. We're going to number it however I like here. Let's just number it 1, 2, 3, 4 going down this way. Okay. You may have a slightly rotated version of this, perfectly fine. At position 1, we happen to have an alcohol group. The OL means I have a single bond to an OH. That's your hydroxy group. And then at position number 3, we have an ethyl group here. We have a carbon and a carbon. Everything else is normal. We're an alcohol here. Again, a secondary alcohol. Okay. Today we're going to be introducing another functionality here. The functionality is a little bit more scary, but we're going to learn some of the basics, some of the naming of this here. Let's just sketch this down here. So there's another family of organic molecules here. We'll call it aromatic. It does have that root word here, aroma. Aroma means a smell, okay? It doesn't mean it actually smells nice, okay? But it turns out this class of molecules here happen to have a very distinctive smell here. The special grouping that this has, the functional group that we're looking at, okay? the functional group that they have is actually a benzene molecule, a benzene functionality. Benzene actually has the molecular formula here, C6H6, okay? We had seen this a little bit in the last chapter, but let's just slowly work up to it now that we've done a little bit more with organic. Let's start off with our saturated molecule. So if I have C6, the saturated molecule here should actually be 2n plus 2. It should actually have 14 hydrogens. So that would be indicative of we have 6 carbons in a chain. We have all the other ones understood here to be hydrogens, so that's just going to be hexane. You'll notice going from this hexane, this alkane, fully saturated, okay, this is containing the maximum number of bonds, maximum number of attachments that we can have. Trying to get it down to C6 with H6, I had to have lost a bunch of hydrogens. There's a lot of degrees of unsaturation. Now, previously we had seen before, how is it possible that I end up losing hydrogens? We saw that every time I form a ring, okay, every time I form a cyclic compound, so far we've only been doing things that have one ring, but we could potentially have things that have multiple rings fused together and all that. Every time I form a ring, I would need to ditch the 2 sides so that I can connect those 2 carbon ends, so that would make me lose hydrogens. The other way we saw we lose hydrogens, we get some degrees of unsaturation, is we form multiple bonds. Again, for simplicity, we only dealt with things that only had 1 double bond or 1 triple bond for alkenes and alkynes. But in this molecule here, we're actually going to form not only that ring structure. So let's imagine I drop those 2 hydrogens, I form this ring. I'm going to have 6 carbons in this ring here. That would now be C6H12. Good, and I'm slowly on my way there. What we're going to do, instead of allowing all these carbons here to hold 2 hydrogens apiece, we're actually going to alternate. Let's make this single bond a double bond. So that would have ditched 2 other hydrogens there. Let's make it another double bond. Let's make it another double bond. That's actually how we got our degrees of unsaturation. Sometimes they even number how many degrees of unsaturation. The index of hydrogen deficiency. This is just for how many times did I lose 2 hydrogens? I got 1 for forming the ring. I got 3 other ones here by forming double bonds. This is the one molecule that we're going to do that actually has multiple bonds. This is actually a functionality for the molecule here. This is the benzene molecule. If you look at carbon making the 4 bonds that it has, it's using 3 of its bonds, the double bond, what looks like on one side, the single bond on the other side. That means I only have 1 extra arm to hold on to a hydrogen there. Okay? So this molecule by itself has already a lot of unsaturation. Okay? Saturated was my hexane. I have lost a lot of those hydrogens there. Okay? So unsaturation. Okay? And this molecule here, very often looks like a turtle. Okay, I like the skeletal drawing of this one here. We have the carbons forming the kinks. So far, this isn't benzene. So far, this is just everything single bonded, just as I started. I still have to put on what looks like the equivalent of 3 double bonds there. Now, this sort of system here shows up very often, where we sort of alternate. It's a double bond, then comes a single, then a double, then a single, and whatnot. It gives this molecule very specific stability. We call this pattern here, we call that conjugation. Just getting used to some of the terminology here. Conjugation is this notion here. We have alternating single and double bonds. Okay. That makes this benzene here very, very stable. Okay. So if you go on to chemistry and you start learning some of the reactions of alkenes, even though this one here is like an alkene, actually with 3 spots that are double bonds, because it has this conjugation, this extra stability, it doesn't behave in the same way that other alkenes do. Okay? One other thing that we introduced on the last chapter here, well, it doesn't necessarily have to be the double bonds in these positions. It's also possible I could have that same 6-carbon ring, but we can actually have the double bonds. Let's say it's this double bond, then single, double, then single. Well, which one is it? I could draw 2 possible Lewis diagrams. If you remember from the last chapter, this molecule also demonstrates resonance. It also demonstrates the idea that electrons are shared, electrons are delocalized over all 6 centers. Okay, so electrons shared over all 6 centers. Usually electrons are paired up. Usually they're sort of stuck in between. They're bonded. They're trying to glue the 2 carbons together. Because I can draw both of these molecules, we know that neither of the molecules actually captures the full idea of this picture, but the real picture here has these 6 electrons, which would have otherwise made 3 double bonds here. Those are actually just swimming around the molecule, which is why very often the resonance hybrid, we usually actually draw it with just an O in the middle to represent that these electrons here can't really put your finger on it. You can't say, aha, you're right there, right there, right there. Those electrons can actually swim around the entire structure. That also sort of goes with what we've been saying. It adds really, really good stability to this molecule here. If you really wanted to name this molecule, we would need to name this one here. Well, our longest carbon chain here is going to be the ring. Fortunately, they just had the 1 ring on us here. There's 6 carbons in the ring. So far I would say cyclo for ring. We would say hexane if it was all single bonded. This is a sort of weird molecule here that actually has 3 double bonds. Now the double bond puts us in the ene family. Just like if I had 3 of the same branch where I say trimethyl, trifluoro, tri something, I'm actually going to say tri of the ene that we have. So we actually have a cyclohexatriene. I'm not going to ask you anything as scary as this, okay? So we're a ring, 6 carbons. There's 3 ene groups. There's 3 double bonded groups. And just like we've done with double bonds, oh, double bonds take priority. We need numbers for them. Well, let's start carbon number 1 at one of these double bonds here. Let's just sort of count around, and we actually just give me the lowest of the numbers. So the double bond starts from position 1, position 3, position 5. You could actually call this here 1, 3, 5 cyclohexatriene. Okay. Now, that's very, very detailed. That's very confusing because we have multiple double bonds here. For us, seeing as it's already been given the common name, this word here, benzene, I'm just going to shorthand all of this part here, and we'll just call it benzene. Okay? We don't even need to say cyclo. That's another very common problem. Benzene, I already know the molecule is a ring, so you don't need to say cyclobenzene. But just like any other substituent here, you can add functionalities, you can add other branches, branching off of this benzene structure, but we're actually going to use the actual word benzene as the family name. Okay. So let's try out some of these examples here. Okay. So remember, it's only a benzene ring when I have either the double bonds sort of alternating or just O in the middle, showing you that the electrons are sort of shared. But we could have sort of attachments here. Let's tack on a few different attachments. Okay. I'll draw 2 for you just for comparison's sake. Let's do F and BR and try to give you some branches. Just familiarize yourself with the different names of the branches. Okay. So when you're looking at naming these molecules here, right away you want to make sure that the thing we're talking about is benzene. This puts us in the aromatic family. That's the special grouping. That's the special stable ring that this molecule has. But it's a substituted benzene. Benzene should have had just hydrogens that are attached to it. I had replaced those hydrogens and I subbed on a different group. Fortunately for us here, those groups there are named just like we're used to. So I have a chloro group, I have a methyl group. This is a 3-carbon group here. This is going to be propyl. So the C for the chloro comes first. But in terms of counting it here, I don't want to start carbon number 1 here, or else it's going to be 1, 3, 4. I might want to start, let's say, carbon number 1 on the bottom, and that way I have 1, 2, 4, which is actually a lower number than counting the opposite way. So with that in mind, let's see if we can get the name of this. So the chloro does come first. Unfortunately, the alphabetizing has it at position 4, so be it. So 4-chloro. We have a methyl, we have a propyl, so we're going to go 2 hyphen with the methyl. And then we have the 1 with this propyl group. All right. And then just to say the family here, the ene part reminds me that there's double bonds. I don't want to say that fancy sort of cyclohexatriene kind of molecule. I'm actually just going to literally use this word here, benzene. We're based off benzene. These are the substitutions that are added to my really stable benzene ring. And again, the most common problem I see people do, people accidentally say cyclobenzene. You don't need to say cyclo because I already know benzene is a ring. Now, in comparison, when you look at this molecule on the right, it looks very similar to the molecule that we did earlier. Also 6 carbons in a ring, also has a bunch of these substituents and whatnot. You'll notice here, I don't have those double bond, single bond, double bond. I don't even have a circle inside or whatnot. So in that case there, this is actually not benzene at all. This is what we've been seeing before. This is just a cyclohexane. It's a ring made out of 6 carbons. Everything's just all single bonded, so our ending is just A and E. So this part here, we do actually need to say the word cyclo. This time I put 2 branches on the top, so we do want to count that position number 1. Aside from that, we're just going to do the alphabetizing. Okay. So if you compare the name here, 1 bromo, we have 1 fluoro. Both of those are on spot number 1. I have an ethyl at branch number 3, and then I have a iodo at branch number 4. Okay. Where previously I can just use the root word benzene for this ring here. Well, my ring isn't benzene at all. My ring is actually just a parent of cyclohexane. So I just put those side by side for you to make a comparison here. It is important for us not just to have the 6 carbons in the ring, but it also does have to have the double, single, double alternating. Okay. One last thing as we look at these benzene structures here. Specifically because benzene reactions are so special, they're in this aromatic family here, we can give some common names to 2 substituted benzenes. So benzene should have 6 hydrogens associated with it, but imagine we've subbed on 2 special groupings. Because benzene is always going to be a 6-carbon ring, again, it's not a benzene until I have those double bonds. I can also represent that delocalization here with the circle here. There's a shorthand way we can say if the 2 branches that we attach, if they're side by side, meaning they're going to be in position 1 and position 2, they could be the same group, they could be different groups, it doesn't matter. Those positions there is referred to as the ortho. Sorry, spell it correctly here. Ortho. That's the O version of benzene. If we have benzene, again, I can use that O in the middle here. If we're in the 1, 3 position, so remember we're going to put position number 1 at one of the branches. I'm going to count around so the other branches occur at a small number as well. If we have a 1, 3 positionality, this is called the meta position. Okay. And then we can have the other possibility here is 1, 4. Okay, just to get you familiar with all the different ways we can draw benzene. I could have drew it with the circle as well. 1, 4 actually implies that these attachments are just directly across from each other here. The 1, 4 positions is referred to as the para setup. Okay, so ortho, meta, para, which allows you to say, for example, how do we draw para dichlorobenzene? Okay, again, we only use this terminology ortho, meta, para for benzene with 2 different substituents, 2 different branches, 2 different new replacements. They are in the para position, so they're across from each other, happens to be 2 of the same chloro branch. You'll notice instead of saying 1, 4 dichloro, para already means across from each other. Let's just sketch our benzene. I can even sketch a sort of end on, okay? And we've actually just tacked on a chloro and a chloro here, okay? Remember, we always number where the branches are, so 1. No matter which way I end up counting around, the other position is 1, 4. So sometimes for di-substituted benzene, benzene with 2 substituents here, we may use the terminology ortho, meta, or para instead. Okay. All right. If you go on to the chemistry of this here, it's very possible to have rings actually fusing together. So again, really, really complicated. When we start looking at different biological molecules, proteins, steroids, they typically very often have functionalities that are rings that are fused together. Not just a molecule with multiple rings, but the rings are actually sharing parts of the molecule. Again, they're not benzene until we have those double bonded positions. So far this is a benzene ring, but it turns out this double bond here is actually shared by the other side here. We very often just give this a very common name here. Let's call this naphthalene. Obviously, there's going to be more chemistry in this. Well, how do we count the lowest numbers if we were counting sort of 2 rings together? But at least for the common name, instead of having something with like pentaene, there's 5 double bonds somewhere in the picture. We're just going to say naphthalene for that one. This one here, again, we have some fused rings. Okay, this is called anthracene. You'll notice for all of these rings here, they don't use the prefix cyclo because the common name already represents the fact that it is double bond, single bond, double bond. That sort of conjugation, that resonance picture here, we already used that as the family name. Okay, So again, practice through some naming of benzene structures and let me know if you have any questions. Thanks, guys.